In this video, we will be discussing a very interesting question of missing Bravais lattices. We have seen in a previous video that lattices are classified into 7 crystal systems listed here as cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. And then these crystal systems are further subclassified into Bravais lattices, which are shown here by symbol P, I, F, and C. P stands for simple, I stands for body-centered, F stands for face-centered, and C for end-centered. Actually, C can be replaced by A or B depending on the situation, and this was explained in a previous video of this series. So, we see that 4 possibilities are there for the orthorhombic crystal system. Others don't have these 4 possibilities. Cubic has only 3, tetragonal 2, hexagonal 1. Why? So 7 crystal systems, if each of them were having 4 possibilities, 7 into 4, 28 possible lattices were there. However, Bravais has included only half of them, 14 of them. So why half the boxes? Why half possibilities have been left out, have not been considered by Bravais, has not been included in the Bravais lattices? So this is one of the central questions which will lead to interesting insight into the definition of crystal systems and Bravais lattices. So let us begin with the first row, the cubic crystal system, and there we have P, that is cubic P, simple cubic, cubic I, body-centered cubic, and cubic F, face-centered cubic. Why not cubic C? Why not end-centered cubic? So that's an interesting question, and we will explore this in a little bit detail in these slides. So end-centered cubic is not in the Bravais lattice. Why not? So I have drawn 2 cubic unit cells side by side with a common face. And I have tried to make these cubic unit cells end-centered cubic by placing additional points on top and bottom faces. You can see I have not put them on all faces. If I would have put them in the centers of all faces, then I would have got a face-centered cubic, which is an allowed lattice in the cubic system. But if I place only on one pair of opposite faces, in this case the top and bottom faces, and I have not put lattice points on the left and right faces or front and back faces. So if only on top and bottom faces I have placed lattice points, I should get end-centered cubic lattice. And it's there right in front of our eyes. What is wrong with this? Why has this not been accepted as a Bravais lattice? Think about this. Pause the video here and try to get an answer. Try to think of your own answer before seeing the development further. Now, if you look carefully, you can identify, you can carve out this red unit cell out of the original lattice points. And if you look carefully at this red unit cell, the two sides on the top face are actually equal. Both of them are half face diagonal of original cube. The third side is not equal, and that is equal to the edge length of the original cube. So this red unit cell, in terms of lattice parameter, satisfies the criterion for an tetragonal crystal system. Two sides are equal, third is not equal, and all angles are 90 degree. So we now have a tetragonal lattice with which has the side length A, which is original cubic divided by root 2, and the C parameter of the tetragonal is equal to A cubic. So we see that n-centered cubic can well be described as simple tetragonal. And obviously, this is also a smaller unit cell. You can easily show that this unit cell has only half the volume of the original cubic unit cell. So then it makes sense to call this or to refer this to this smaller unit cell and call this a simple tetragonal. But we will soon see that situation is not that easy. So if we see now, I have deliberately placed cubic C. This is what we tried to construct, but we found that no, we can describe this as tetragonal P, which is already there in the Bravais list. So there is no need to put this additional 15th Bravais lattice as cubic C. And tetragonal P, at least in terms of size, is a better description than cubic C. But as I told you, situation is not this simple. Because let us try now to apply the same procedure to an FCC lattice. Instead of drawing an end-centered cubic lattice, I have now tried to draw a face-centered cubic lattice. Of course, it's not complete face-centered yet. I have not put lattice points on the front and back faces. But please do so. Imagine that front and back faces are also centered. Only for the clarity of diagram, I have not done it here. So assume that lattice points are at corners and assume that lattice points are at all the centers. If we apply the same geometrical construction, if we apply the same logic and identify a unit cell, this red unit cell in this lattice, can't we do this? If it was allowed there, if it was allowed for n-centered cubic, it should be allowed for face-centered cubic also. And if it is allowed, then face-centered cubic lattice appears to be body-centered tetragonal. Note that if we are working with the original face-centered, then the original face center of the common face now becomes the body center of my this new red unit cell. Then we come to the surprising conclusion that cubic face-centered cubic should also be called tetragonal I or body-centered tetragonal. So just like we crossed out cubic C to call it tetragonal P, simple tetragonal, we should actually cross out F also, cubic F, face-centered cubic, and call it tetragonal I, body-centered tetragonal. You can see we are now into a difficulty because that when we crossed out tetragonal cubic C, we were happy because we didn't want cubic C. But now we are crossing out cubic F, which was there in the list of original Bravais list. So in fact, we are now reducing the number of Bravais lattices from 14 to 13. Have we made a new discovery? Let us look at a bit of history of Bravais lattice. Auguste Bravais in 1850 showed that there are 14 different lattices and in his honor we call these as 14 Bravais lattices. But even in 1850, Bravais was not the first one to attempt to count lattices. 15 years before him, Emil Frankenheim made the first attempt to count lattices, and he had counted as 15 lattices. He made a mistake. He overcounted and got the number as 15. Bravais was clear with his work and corrected this mistake and got the correct number to 4 lattices. But history has been so unkind, so unfair to Frankenheim that his name is not associated with these lattices. I feel that at least the lattices could have been called Frankenheim Bravais lattices to give some credit to his attempt. However, just for a single mistake, for one additional lattice, his name has been wiped off from the history of crystallography. Not only his name, I did not find his photo on the internet. Now, today, in this discussion, we have shown that cubic F should be tetragonal I. So we are reducing the number of lattices to 13. Are we making a new discovery? Are we now going to erase Bravais' name from the history of crystallography? This is an interesting puzzle. This is an interesting conundrum which we will discuss in a subsequent video, and this will throw a lot of light on the definition of and classification of these lattices. Thank you.